look for clumps of BHB stars to see if we could pick up a metal pore cluster or two, and we didn't see anything. But no, at the moment, we're not confirming any of those clusters.
None. Oh, wow.
Not at the moment. But
Okay.
we're having another look with, the EDR3 data, and, we're going to have a definite deeper look. But unfortunately, our survey does not reach below -2 degrees.
Okay, we should move on. Let's thank Mike again. We've got at least 2 joules scheduled for the tea break, but we have Tim Beers who's actually going to start a revolution. So this will make the afternoon very exciting.
Prince in the Revolution. Okay. So we're going to check the first slide. Is that?
It's live, so hit it again.
This one.
Yep. You're good? Okay.
I'm good. Okay, so first I have to apologize. I've miscounted the numbers of stars in my title. I've actually underclaimed, and hopefully we'll demonstrate that we overperform. So it's more than 500,000. I'll show you where the error was made. Photometric metallicities used to be a pretty bad word among those of us who say we could do better with medium resolution spectroscopy, which includes a fair number of people in this room. But it turns out that with careful work, mostly of others, but I got dragged into, in particular, zero pointing of individual filters properly, which is hard to do over large swaths of sky. You can eke out equally good metallicities and, I would argue, individual elements for a number of them from properly selected filters, in particular narrowband filters, which I'll emphasize. And so I was surprised. It works. It works demonstrably well. And I'll just try to touch on why. So here's a view that many of us have seen before, but I brought this view up for one good reason. There's a telescope here, right? That's some bizarro interaction of these overhead lights, which, by the way, should not be on in front of a screen. You're astronomers, shame on you. Get those off. First thing I have to do at every physics colloquium, adjust the lights. They say, why are you so particular?
Must have been a forest fire. I mean, yeah, it's still very wet.
All right, so tune this up. It doesn't look that way on my laptop. The point is, there's a telescope that virtually everyone here has probably used. If they're an observer, here's a telescope which you thought about using but probably didn't get around to. And here's the dome of the Curtis-Schmidt telescope, which CS has special meaning to George Preston, Steve Sheckman, and myself, and others who don't know where it came from. It stands for the telescope. We should name stars after telescopes, not after people, my view. Here is what's inside that dome. That's the Curtis-Schmidt. And this is an RA and deck, an equatorial mount, which means that if you're going to use this telescope, you're in for an adventure. But when I take pictures of these kind of telescopes, they always put them in very comfortable viewing positions. This is the guider telescope. You can just imagine doing a Hubble and standing up there and looking through and doing your hand guiding. It doesn't work that way. It just doesn't. Because it's equatorial, you point in any direction in the sky, and it's going to be worse positioned than that for guiding. You're going to be eating the floor. I mean, literally 6 inches off the floor. I can't do it nowadays. Or 15 feet up on that ladder above the observing floor. Neither one of which are particularly conducive, especially in the middle of winter. But that's the southern version. That's the northern vision at Kitt Peak. That's the Burrell-Schmidt. I like the paint job on that much better with the brass fittings. But again, a very comfortable position for guiding, right there. Well, anyway, so my point is, I asked George one time, we need more plates. And I won't tell the joke that's surrounded, but his
I'm gonna
response.
tell a story about you.
Okay, but his response basically said, if you want more plates, you're welcome to go get them. And so Steve arranged to go down with me to Tololo, taught me how agonizingly difficult it was to get these plates. And so I learned from the pros. About halfway through my first run with Steve, I walk over to the 4-meter. He's sitting around playing cards with the night assistants who weren't busy doing whatever. I walk in and they say, who's this guy? And Steve says, auto guider. You remember that, don't you, Steve? Oh, well, then you should be embarrassed. But anyway, so here's the basic problem, and we're all guilty of it. I apologize, it's a worn out metaphor perhaps. But when we look with spectroscopy at our thing we call a galaxy all around us, we always emphasize one feature or another. And depending on what you look at, you come to different conclusions. And you see labels, which I won't go through. But there have been samples over the years that have been interpreted in different ways, depending on how the stars were selected. And in fact, that's not the way to do it. Those are, again, just figures. Well, look at this. We can explain that by this and this. We can explain this by this and this. The problem is you're assembling a puzzle with, a couple 100 billion pieces, right? And you're doing it in slices of 100 or 1,000 at a time, usually heavily selected in one fashion or another. Wouldn't it be great if you had a picture on the front of the box? Imagine doing a 200 billion piece puzzle and not knowing what the picture is supposed to look like. 1,000's hard enough. 200 billion plus is virtually impossible. So it occurred to Do-Kun Ahn. Some of you know Do-Kun. He's now in Korea at Iwa's Women's University, that we could do a better job. And it comes from photometric metallicity estimates. And the reason Do-Kun, his name comes up, is he spent a lot of time working with Mark Pinsonneau when he was doing his degree at Ohio State, calibrating fiducial sequences of filters. And even with moderately broadband, like Sloan filters, UGRIZ, if they're well described by the appropriate fiducial, you can squeeze out a little more information than you can from just like broadband UBV. And so here's basically why it works, and I'm jumping ahead a little bit. If you choose filters in the right way, and here you see a couple of what I describe as narrowband filters, one around the calcium H and K, one around H delta, one around the G band, you can see that those individual features potentially make a big impact on the amount of flux that comes and goes out of that filter. This is the Sloan G band, which unashamedly, I and others have also used for metallicity estimates because it was better than the Johnson bands. But still, you can see why it's problematic. It's so big that you can have variations that are just undetectable, especially at low metallicity. So wouldn't it be nice if you design filters where you want them in the first place, which is around the prominent stellar features? And people have done that. And so in fact, this is from a paper I'll be relying on, but you can look it up. It's published now by Huang et al. 2022. These are surveys, and I apologize, it's too small to read for some of you, which are using narrowband filters in combination, generally with wider band filters. And so SkyMapper, you've already heard about. Pristine, you've heard about. Those are using, in this case, say Pristine 1 filter, which is not exactly in the right place, but is closer than some others. It's a little bit to the left of the calcium K band, in my view, of where it should be, but okay. SkyMapper has two moderate filters around calcium K, one to the U, a little bit to the blue. It's okay. The direction we're going, and I'm going to show some data from, are two surveys called J+ and S+. Two telescopes, essentially identical 0.8 meter telescopes, one in Spain, one in Cerro Tololo. 85, 9,000 square degrees on the sky, north and south, down to 21st magnitude, with 7 narrowband filters, 5 wideband filters. And that combination, it turns out, will be very useful.
What was that 9,000 square degrees? What
That's how much coverage the survey.
in the survey?
Yes,
Okay. By
Yeah.
those telescopes. Okay.
that's right. So some of those surveys, well, one hasn't even started, but the others are about halfway through.
Okay.
Okay. All right, so here's just an example of what you can do, even without Gaia, but you can do it better with Gaia. And that is, this is the Sloan data set. So we're talking broadband filters, but it illustrates it fine. So Sloan Northern Hemisphere coverage, you see these two lines here? Those are the lines within 30 degrees of the galactic prime meridian, right? The 180 to 0, okay? And when you're within 30 degrees, you only pay about a 10% penalty in terms of deriving the rotation velocities without a radial component, because you have no radial component of proper motion. So you can do it from proper motion alone. And Sloan measured proper motions. So we can do it with Sloan proper motions. So what that means is you can ask yourself, well, I'll make my best metallicity estimate, and this is just a map from Sloan filters down to about minus 2.5, which is not bad, but not as low as you'd like to go. And then you can look at how the galaxy changes as a function of both metallicity and rotation velocity, the picture on the cover. And so without going into detail, I'll show one of them in detail. Here's as a function, and this is rotation velocity as a function of Fe over h as a function of distance above the plane. So you start dominated by disk-like stars, and you get more and more halo stars as you get farther away. Okay, but let me show you something so you don't have to squint. So here's a map. Here's the picture on the front. All these things that are labeled are features that were identified in the recent literature or the last decade or so, basically from spectroscopic samples. And people argue back and forth and back and forth. Is the halo, or is it complex? Or, you know, this goes back and forth for a long time. Imagine picking -2, all halo, some would say. And you just integrate across radial velocity. And you see you got at least 3, possibly 4 components, depending on how metal weak the thick disk is, that creep in. So that if you're not taking into account the rotation of the population, you're taking spectroscopy, you're always combining samples. And that's just one component of motion, right? So you can see where all the debates, many of the debates could have come from. And the nature of this changes as a function of distance above the plane. So, and where in the galaxy you're looking. So in other words, without a picture to guide you, if you saw this 20 years ago, you might say, well, gee, why don't we go look for stars in this range of metallicity and rotation and see what we find spectroscopically. That wasn't how it was done. Hence the debates. But we should do it this way or something similar in the future. Okay, and again, you can fit Gaussians to your heart's content. There are precise statistical means, by the way, Mike, you might be aware of them, for telling you when you have too many Gaussians. Okay, and these, right, you can actually work that out. Okay, so here's another approach, and I just want to show 2 approaches. One is by a former student of mine who finished last year and jumped ship to go to the financial industry. I'm sure he's doing very well, holding hands for people who've lost money. But in any case, what he did before he left is he developed a sophisticated neural network approach using the Southern data, S+, that can obtain estimates, of course, of stellar parameters, as a minimum, but also carbon to iron, based on the combination of narrow and medium band. All right, well, the pros of this is it appears to work very well. We know it goes down, we've tested it down to at least -3.5. It might work to -4, but it certainly works to -3.5. Okay, and the technique he used, I'll just mention it because it's clever, is robust to photometric errors, which has always been the bugaboo in individual filters, especially if you have one metallicity sensitive filter and you get the wrong data from that particular star, you're screwed, right? You wouldn't even recognize it, call it what it wasn't. But this avoids that. It is somewhat complex, which is not ideal. And we're still working on extending it to other elements, but the essence is really cute. Whoop. Oh, so this is just where the data come from. This is Sloan Stripe 82 in galactic coordinates. So that cuts across, it's equatorial, but it cuts across a big range of galactic longitude and latitude. But what he does, every dot on that page is an individual neural network combination of filters. You say, well, professor, how do you know which filter to combine? You don't, because every narrowband combination with either another narrowband or a broadband carries some information on stellar parameters. Some better than others. So the usual approach has been to say which one is best, define a polynomial, and run with that. That's what SkyMapper did originally for their metallicities. But it turns out you don't have to do that. So what he did is he defined, you have 12 filters. So that gives you tens of thousands of possible combinations. So you choose something like 10,000 possible random combinations. And you train your neural networks with the information that the ground truth answers to. And then you ask the neural networks to form a committee and to decide which of these filter combinations actually look best compared to the training objection, and which are second best and third best and fourth best and second for a given star. You do that once you're trained up and apply that to your data set. And let's say you had a cosmic, or whatever the origin was, just landed smack in the middle of the calcium H and K region, just you're totally wrong flux. That's okay. You have like 9,999 other filter combinations that you can choose from. So you'll take the second best or the third best. And you will know by looking at those combinations of filters how confident you should be. Okay, that's a huge advantage, it turns out, because you make very few, or at least a usefully small fraction of what I call catastrophic failures. And so catastrophic failures means one misestimation, generally on the low side of F over H, could maybe impact your estimate from half a dex to 1 dex. That's really what you expect to see when you make a mistake, because there are so many metal-rich stars that the tail of errors stretches into the metal-poor region, right? So you just have more chances to make an error of moving a metal-rich star into a metal-poor star designation. That's the direction you expect. So you fight it by having these committees would say, well, wait a minute. If you're going to go with that metal poor estimate, we got another couple thousand committee members here that think that that's way out of line. So let's discard that and go with something everybody can agree on. That's what the committee of committees does. All right, so I compared this to Pristine as best we could. He's on the paper. I mean, one of the Pristine authors is on the paper, Cordopadatus. And in any case, so we looked at stars less than -2. And of their, and this is a few years ago, so they might have improved things. Of their stars that were photometrically claimed to be less than -2, about 30% of them were wrong by 0.5 dex or more. That's a catastrophic failure. Something like 6% were wrong by a dex or more. Okay, that's a catastrophic failure. One of the reasons you do these things is to get the picture on the box correct, and that influences the picture on the box. It also really influences the tail of a MDF. That's what you're trying to get. Here's what we get with this thing was called Sphinx. Same setup, less than -2, we get 6% with catastrophic failures of 0.5 dex, and only, well, less than 1% greater than 1 dex. That's a huge improvement for certain problems. Okay, so
it's a neural network index of some sort. I mean, how do you establish a number for this?
Well, it's not a single number. Basically, the neural network, we can talk about it later. This is a little more complicated than I want to get into, but the basic idea is you tell the network what these filters should look like at a given set of stellar parameters. And it evaluates how close a given star is to those parameters. Okay, because it's looked at other stars in those filters. Okay, how it does it is sort of different. Okay, but it's a black box, but it's a well-trained black box. Okay. Anyway, so there is an alternative, which is easier to understand. Yang Huang, who is very bright in China, has also taken the view that a combination of narrow and medium band filters, we tested this first with SkyMapper, little v and little u, along with a broadband color, just the Gaia BP minus RP, can also give you accurate estimates of temperature and metallicity, also logarithmic, if you use appropriate polynomial fits to spectroscopic samples. So what that means is looking at high res, mostly high res, a few medium res calibrations, looking how this combination of filters, just a limited combination in this case, works. The pros are the Gaia colors, this bit here, is very precise. It also works down to at least -3.5. It's inherently simpler to apply once you properly 0 point the filters, and I emphasize that at the beginning, because the SkyMapper stuff does have a lot of variation. And so the cons are it's probably not as robust to catastrophic failures, but that might be okay for some applications. And we have yet to extend it to other elements, but we will. We're in the process. So here's what SkyMapper looks like. A lot of people think SkyMapper is done. It's not done. Just the people who were working on it were done. What I mean is the Australians chose not to fund the people who were doing all the work, and so they had to scramble. All right. So in the end, this is the shallow survey. That means 6-second integrations. Their full integrations are coming out shortly, a couple extra magnitudes. So everything I say is based on those. But anyway, you get polynomials. And these are combinations, little u versus minus GBP versus the colors. Dwarfs and giants get treated differently. These are the giants. What you're going to notice is the colors separate out very well. They're color coded by metallicity. So you actually can fit to star's position on such a diagram, essentially read off the metallicity. That's what I mean by simple. Okay. And here's the sample. Here's what you get. Here's where I miscounted. Applying this to the southern sky, we have over 20 million stars. This was with DR2, that's the shallow survey, and EDR3 from Gaia. So you can see as a function of metallicity, you can count down. In total, there's over 20 million, but by the time you get down to VMP stars, here's where I miscounted. I just added those two numbers, and that was roughly 500,000, or on the brink of it. But that was only between -2 and -2.5. You keep going down, there's 730,000 stars here below -2, 258,000 below -2.5, and 27,000 below -3. And you say, how sure are you about those stars? Yeah, we're pretty damn sure. And the reason we're sure is we looked. So this is comparing here and here to medium resolution spectroscopy. The spectroscopic determination is down here, photometric right here. The eye will be drawn to the outliers. You notice how many of those outliers have little blue little blue stars around them? Those are known to be carbon enhanced. Of course, those are problematic because particularly for giants, the carbon enhancement has squeezed from the blue of the calcium K, the CN band, has squeezed into the calcium K region and started taking a metal poor star and made it look like a metal rich star. So with that exception, if you don't know carbon, you have to be a little bit wary, but it works. That's exceedingly remarkable behavior. You know, we looked just below -1 in this case, but it went all the way down to -3.5. This is high resolution. The blue stars here are LTE, so that's probably not particularly fair because they have corrections relative to, they're non-local thermodynamic equilibrium abundances. So those, I didn't want that in the figure, but they left it. But anyway, the red ones are high resolution. So the bottom line is you calculate the dispersions. You're welcome to spend another 2 decades measuring medium resolution spectroscopy if you want, but I'm not going to do it. Right? Because this is better, faster, and works just as well. And now we can actually calibrate these things, S plus J plus, with the multiple narrowband filters to include other elements. We already can do carbon. We've already done that. Whoop. We've already done that. And we're soon to calibrate magnesium, calcium, and nitrogen. And I would say for 90% of this chemical evolution questions that people ask, that'll be plenty. Keep you busy for a couple years at least. And here's just a teaser. This is about 2,000 square degrees of northern sky from J+. That's C over FE as a function of FE on H. And everything above this line is what we now consider to be carbon enhanced metal poor star. And you know how to get that? We took a picture. Well, a bunch of pictures, but still, didn't have to take a spectrum. And now you know which ones you want to take spectra of. That's because you've looked at the front of the box. That's a better way to do science. Look at the sheet at the front of the box. Okay, so finally, this is the near photometric future. We will soon, where soon is measured in probably a year, have photometric metallicities for hundreds of millions of stars, because these surveys will have been completed and we won't just do the little applications that you've seen. They'll be as good or better than medium res spectra, 0.1 to 0.25 dex. Maps of stellar populations will show us the picture on the front of the box. Full space motions can be derived with proper motions and obviously radial velocities, 27 million new or total radial velocities in DR3. And of course, what you really want is detailed follow-up at high res. That's where you want to spend your time, especially the ones below -3. And basically, all these directions are going. And of course, Alistair will give me another 10 seconds because he wants to do something similar by extending DES with a narrowband filter. And ultimately, we're going to do the same thing with LSST. So let me stop there.
Questions?
So where is this, what is this J+ survey and who's running it? And
Yeah, see, that's the problem. They've been publishing papers. You just haven't been reading the right papers. The J stands for Javalambre, and that's an observatory in Spain. Okay. And those are the same people who are doing JPass with 47 narrowband filters, but they had to run a test case. Galactic astronomy is always a stepchild to the cosmology. They want to do photo redshifts, right? They want to do photo Zs, but they had to prove the concept. So they said, well, we'll do something easy like measuring stellar populations. So that's what they've been doing.
And so this is their published data they've already.
Yes. Yeah, but it's partial. I mean, they've done 1,000 square degrees, and I just lifted that. But the same filters, same telescopes are used at Tololo. When you're next there, look for the mushrooms. They're all over the place. But one of those mushrooms is the S+ telescope, automated. It's about 40% of the way through. Sorry, excuse me, 60%. There's 40% remaining. So it's already got 4,000 or 5,000 square degrees. We're just trying to calibrate it right now. We expect to do that in the next few months.
And the same filters more.
Identical.
Okay, well, since you mentioned it, Tim, 1 week ago, I ordered the
good.
HMK filter. The queue for construction, so we should have it here for 2023 ACS.
Excellent.
It's the same as the pristine, the passband is the same as the pristine HMK on CFHT. That was delivered.
There were better choices, but that's okay. It's still.
We like it.
Yeah.
No, it has to be wide because it's in a fast thing. You don't have a choice.
You can't make it much narrower.
Yeah.
What's
Right.
the forward maximum of the band?
100 angstroms. 100.
About 100.
100?
Yeah.
And centered on the
They're
space
very
between them,
steep-
between
it's
them?
very- They can make narrowband filters with very, very steep sides and flat tops.
I see.
So it's basically forward half maximum, 100 angstroms, and the flat top is about 80 angstroms.
Yeah.
So you can accommodate some radial velocity change and get both H and K.
Right.
And what's the transmission of the
Oh,
filter?
they're 95%.
Oh, yeah.
Yeah, that's quite good. Yeah.
Really?
It's quite good.
Wow.
Yeah. Well, that's excellent. And I should also mention, because you'll be using a bigger telescope. S+ is 0.8. Right. The point is, you'll be getting faint stuff, but the S+ will target the entire DES that already is, the whole footprint, with exposures that will go as short as 1 second That's not standard. That's an ultra short, but they will do it, have been doing it. And that'll give you non-saturation up to 8th magnitude. So you go from 8th magnitude out to wherever your limit is, 23, 24.
How did you choose the elemental abundances that you were going to concentrate on?
Yeah, those seemed like the most obvious just to people who wanted to model things. And
Would you consider manganese? Manganese has been shown to be.
yeah, I'd consider a lot of things.
Choose manganese.
Yes, yes, yes. That can clearly be accomplished in other surveys. Probably not in this one, because there's a lot of science besides what I want to do that people are doing with these. But one I really miss is sodium.
Sure.
We avoided the sodium doublet because everyone knows you can't measure sodium for stars from medium resolution spectroscopy because of the interference you get from interstellar. But you know what? We figured out how to beat that. Yeah. And so you can do that because there's a very well-behaved a relationship between the strength of the interstellar and line and distance that you can estimate very well with Gaia. And so you can actually fit every line of sight and say how much is there, calculate it, subtract it out of the index. That's how much flux is interstellar. What's left is stellar, and you can do that. We're doing that now, but we don't have a narrowband filter.
One last.
Well, if this is the answer to, how will the unbiased against metal four stars will do
Sure.
an H&K survey.
Essentially,
The foot of the BBS footprint.
yeah, you can do it easily,
Get the fact.
easily. It works.
Okay, that's the end of the session, so let's thank all the speakers again.